Hello again, Lee McIntyre here with some more insights into the special theory of relativity. Let's get into it. In this video, we are going to solve some problems in relativistic mass, momentum, and energy using the velocity triangle. Let's start with some classical definitions so we are all on the same page. First, we turn Newton's law upside down and define mass as the resistance to acceleration. We will examine this in much greater detail in a later video. Momentum is the integral of forces over time to affect a change in velocity. It is a spatial vector in the direction of the applied force. Finally, energy is the integral of force times distance, for potential energy also equal to kinetic energy. In Newtonian physics, energy is a scalar. We shall see that this is not true in special relativity. First, we'll show how to solve simple problems involving proper source measurements of temporal momentum only, without spatial momentum. For relativistic mass, momentum, and energy using the velocity triangle. It turns out that the velocity triangle solves mass, momentum, and energy problems as easily as it solves problems of displacement, as we have seen in the earlier videos. First, we set up a velocity triangle for S0 in red, receding from S1 in blue to the right at half the speed of light. This corresponds to a Brem velocity angle beta of 30 degrees. Next, we assign S0 a rest mass of m0. We multiply S0's proper temporal velocity at the speed of light in the direction of its local time vector by m0, instead of elapsed time t as we did for displacements. I call this quantity the temporal momentum m0c in the direction of the unit vector t0. m0 is at rest in S0, so the spatial momentum p0 in the x direction is 0, making the temporal momentum proper in this case. Multiplying the temporal momentum by c yields Einstein's famous equation for energy. Note that while energy was a scalar in Newtonian physics, it is a vector in the direction of local time in special relativity. Just as we projected a proper displacement in time in S0 onto another reference frame as displacements in time and distance, we do the same with proper momentum to project S0's temporal momentum onto S1's temporal momentum component M1c, also equal to its E over c. With the spatial component of momentum P1 in the x1 direction. Note that the M0 term in both E1 and P1 have been increased by the cosine beta term in the denominator, causing S1 to infer that the S0 mass is greater in its interaction with other bodies in the S1 reference frame. We can now gain some insights here. First, the energy relationship between S0 and S1 multiplying S1's temporal momentum component to obtain Einstein's familiar equation in terms of m0. Next, the spatial momentum term, just the temporal momentum multiplied by the sine of beta. Just as velocity was the ratio of spatial displacement to temporal displacement, it is also the ratio of spatial momentum to temporal momentum equal to the sine of beta. And the proper temporal momentum of S0 is the square root of the S1 temporal momentum squared less the S1 spatial momentum squared. Kinetic energy K over C is the difference between E1 over C and E0 over C. As beta tends towards zero, by trigonometric identity, the cosine terms tend towards sine squared beta over 2, and K1 tends toward Newtonian kinetic energy as the small angle approximation. Next, we're going to tackle transformations of source measurements with both temporal and spatial momenta. We see that the Lorentz transformation of momentum is identical to the transformation for time and distance, except that the proper velocity c in the direction of local time is multiplied by mass rather than elapsed time, and the spatial component is p sub x. Since we're going to define x in the direction of motion, orthogonal momenta in the y and z directions are zero. We will omit the x subscripts and deal only with p equal to p sub x in its frame of reference, unless there's a reason to include the orthogonal velocities. Let's go back to our original S0 and add a spatial momentum P0 to the temporal momentum. This makes it a measurement. We locate a point on the S1 time axis equal to M0C and erect a temporary x-axis. We proceed from the measurement M0C parallel to the T0 time axis to intercept the temporary x-axis. Then an equal distance parallel to the T1 time axis to locate S1's measurement E1 over C and P1. And that is all there is to it. This is the axis of symmetry solution we developed for temporal and spatial displacements in previous videos. Next, we're going to look at photons, packets of light. Photons are a special case. We're not going to get into wave-particle duality, but photons do have momentum and energy and can interact kinematically with matter. The energy of a photon is Planck's constant h times f, the frequency of the photon. Since the velocity v of the photon is the speed of light in all reference frames, The momentum of the photon is also equal to its E over C, and its rest mass is then zero because it can't be at rest in any reference frame. However, it does have an effective mass equal to hf over c squared. This is what gravity interacts with to bend light. The Lorentz transform of a photon's equal values of energy and momentum to another reference frame results only in a Doppler shift of the photon's frequency, while retaining equal values of temporal and spatial momenta, and velocity p divided by E over c remains equal to the speed of light. Now let's solve some kinematic problems, that is, the energy and momentum of bodies before and after a collision. We're going to take the collision to be perfectly inelastic. That is, the bodies will adhere together. We are going to first look at this from the center of momentum reference frame, in which the bodies have equal and opposite momentum. We're going to begin with an observer at rest in the center of momentum reference frame S0 in green. We are doubling the scale to make the transformation of m equal to 1 easier to see. The observer is being approached by a body of mass m from the left at a speed of 86% of the speed of light, the velocity angle of 60 degrees. This is S1 in red. The observer is being approached by a second body, also of mass m, from the right at 86% of the speed of light, a velocity angle of negative 60 degrees. This is S2 in blue. S1 contributes a temporal momentum of 2mc to S0 and a spatial momentum P01 of 1.732 m to the right. While S2 also contributes a spatial momentum equal to 2mc and a negative 1.732 m spatial momentum to the left. Before collision, S0 measures a total E over c equal to 4mc and a net momentum of 0. After collision, the two bodies come to rest in S0 with a rest mass of 4m. E0c is conserved as the sum of E01 over c and E02 over c equal to 4mc, and P0 is conserved as the sum of P01 and P02 equal to 0. Now we're going to examine the same problem with unequal momenta. We are returning the scale to 1x to accommodate the larger numbers we will encounter in this problem. We set the observer up at rest with mass m in S1 before the same collision. We rotate S1's reference frame to the vertical and delete S2. We add S0's measurement of S2 from the previous problem, which was a temporal component of 2mc and a spatial momentum of 1.732 m negative, moving at 86% of the speed of light in S0. We transform S0's measurement of S2's energy and momentum into S1's measurement. And obtain a temporal momentum of 7 mc and a spatial momentum of negative 6.928 m to the left at a velocity v10 of p10 over e10 of 99% of the speed of light. This is the relativistic additive velocity for S1's velocity of 86% of c with respect to S2, and S2's velocity of 86% of c with respect to S0. The total momentum S1c's is negative 6.928 m to the left, and a total E1 over c of 8 mc. The total of E10 over c contributed by S0 plus E1 over c from the mc at rest in his reference frame. After the collision, those quantities are conserved with two joined masses having a temporal momentum of 8 mc and a spatial momentum of 6.928 m, retreating to the left at a velocity v equal to p divided by e over c of 86% of the speed of light. No more difficult than the center of momentum solution. Now, finally, we're going to see how a photon interacts with an electron in Compton's famous electron scattering problem. The math here can be tricky solving for the unknowns, but I'll walk you through it. This is a three-dimensional problem with time vertical and the xy plane horizontal with x to the right. The problem begins with the photon at the left with the frequency f, with E over c and P sub x equal to hf over c, where h is Planck's constant. The electron is at rest at O, with its temporal momentum equal to m sub e c and its spatial momentum equal to 0. There are no momenta in the y or z direction. The photon strikes the electron at O, imparting energy to the electron, which departs O along the path OA with some momentum. The photon departs along path OB with E over c and momentum reduced by that gained by the electron, which manifests itself as lowered frequency f prime. Alpha sub 1 and alpha sub 2 are the angles of the electron's path OA and the photon's path OB with respect to the x-axis. E over c after the collision must equal E over c before the collision, with the electron gaining the energy lost by the photon. The sum of the momenta of the electron and proton in the x direction after collision must equal the momentum of the photon before the collision. Since there was no momentum in the y direction before the collision, the electron's momentum in the y direction must be equal and opposite to the photon's momentum in the y direction. Beta is the velocity angle of the electron, the sine of which equals the electron's total P divided by E over C. I'll let you study this a bit, as it is a busy slide with a lot of moving parts, no pun intended. Writing out the three equations for E over C, P sub x, and P sub y, we find we have four unknowns. Beta, the velocity angle of the electron. F prime, the photon's frequency after collision. And alpha sub 1 and alpha sub 2. But we have only three equations. We will solve these three for F prime, the frequency of the photon after collision, in terms of alpha sub 2, the photon's scattering angle. First, we eliminate alpha sub 1 by solving the momentum equation for P prime x, P sub x for cosine alpha 1 and P sub y for sine alpha 1. We square both equations, then add them. We can then set cosine squared alpha 1 plus sine squared alpha 1 equal to 1, thus eliminating the alpha 1 term. And we wind up with the equation shown. Next, we eliminate the beta term by solving the energy equation for the cosine of beta, and applying that to the above equation to get the relationship between alpha sub 2 and F prime. We simplify this by converting frequency to wavelength lambda equal to the speed of light over frequency. And after some trig identities, we find the final relationship. We see that the greatest increase in photon wavelength, which is the greatest decrease in frequency, occurs when the photon is scattered 180 degrees straight back. In summary, special relativity increases the mass, energy, and momentum of colliding bodies by the relative velocities, but it is thereafter just a matter of conservation of energy and momentum. The best way to understand mass increase is to consider yourself going down the road at 60 miles per hour when you are sideswiped by an 18-wheeler who made a careless lane change. It's going to do some damage to your car, but you are both likely to be able to drive off after exchanging insurance cards because your two 60-mile-per-hour momenta were mostly parallel, and only the slight lateral velocity caused the damage. This is the equivalent to the classical world of low velocities, where all the temporal momenta mc are to a high degree parallel. Now consider that same truck colliding with you at 90 degrees, both of you going 60 miles per hour. The truck's 60-mile-per-hour momentum is now focused directly at you, and you are certainly not going to continue on your way after that collision, except to the hospital if you're lucky. This is what happens in a relativistic collision when the temporal momentum mc plays a significant role. I hope you enjoyed this presentation and perhaps learned some things you didn't know about the special theory, the Lorentz transform, and mass-energy relations. If you want to learn more, read my book, Riding on a Light Beam. You can purchase it from Amazon or via my website shown. And don't forget to press the like button. It helps to make this YouTube presentation more widely available.